So this is the first part of 6.2. It's exponential models. We've got some formulas here we're going to use. And here, the I can statement's a big deal. It's writing exponential models in different ways to solve problems. So the task of this question here is to rewrite an exponential function to identify a rate. So let's start off with the details. They say in 2015, the population of a small town was 8,000. The population is increasing at a rate of 2.5% per year. Write an exponential growth function to find the monthly growth rate. So what we're going to do is we're first going to write it as we know how to write it. And we're going to use the amount after time passes is the principal times 1 plus r to the t. And here this is going to be in years. All right, we're going to start off by doing it in years. So the amount after some time passes is the principal, which is 8,000 times 1 plus, we have 2.5%. This is kind of a big deal. It's 0.025. Milbrath has done this for years. And probably 1 in 4 kids cannot write a percentage as a decimal correctly. So 1 plus 0.025. And then we have to the t. So we'll clean this up a little bit. We'll have 8,000 times 1.025 to the t. And again, the way this one is written is time is in years, because I took the per year idea. Now, using the fact that 1 year is 12 months, rewrite part 1 to be a monthly equation. So I want to create something so that I feed it months instead of years. So I think about how many months per year. There are 12 months per year. That's kind of a kicker on this, 12 months per year. So I'm going to be changing the exponent a little bit. I'm going to be feeding this thing months. Now, this was a rate of growth based on time being in years. But if there's 12 months per year, it's kind of like something that we were doing yesterday. I'm going to divide by 12. Because now if I hit this thing with a 12, like if I feed it, let's say I feed it 24 months. Well, 24 over 12 is 2 years. Awesome sauce. Okay, see how that works? I fed that thing, I put in divide by 12. Now, what the state of Tennessee sometimes likes to do is they like to take that 1/12 and move it inside. And leave the t outside. So how did Milbrath do that? Milbrath did that based on this property here, a times b to the x. I'm allowed to move exponents in, and I can move part of an exponent in, a to the x times b to the x, and I can leave part of it outside. I can leave the 1 outside. So I'm moving that 1/12 inside. Now, let's do a quick rewrite here. Let's go to our calculator. You can type this in decimals too. I don't need the 8,000, sorry. I need to know what 1.025 to the 1/12th power is. Now it's about monthly. It's 1.0021. So this is about 8,000 times 1.0021 to the t. And now the time is in months. All right, moving forward. That is a you try it. Quarterly, there are 4 quarters in a year. You do the rest of it. Here's the formula for compound interest, and there is a whole bunch of stuff here that you need to write down. A whole bunch of stuff. This is the formula for compound interest. The amount after time, it just has an a there. It should actually be a sub t. The amount after time is equal to the principal, which is the initial amount invested, times 1 plus r over n to the nt. Now, N is kind of a special number. It's the number of compounding periods per year. And again, there's a lot of stuff here you need to write down. So let's talk about N. Compounding monthly. There's 12 months in a year. N is 12. Another big word is semi-annually. That's 2 times per year. Happens twice a year. You might see quarterly. N is 4. You might see somebody say yearly. Well, then N is just 1. Another type of interest that's done often, especially in the world of credit cards, is daily. N is 365. So those are the types of compounding that you'll often run into. And again, this is the compound interest formula. All right. So moving forward to do one. You recently discovered that your ancestor invested 10 cents in 1812. Now, 10 cents, by the way, 10 cents is $0.1. I'm going to convert that to the dollar decimal, all right? Into an account that pays 5%, so the rate is 5%, which is 0.05 as a decimal. You shift the decimal 2 places to the left. Compounded quarterly and is 4. Now, sadly, so you were left, your ancestors invested 10 cents in 1812, you think it's not worth anything, into an account that pays 5% interest compounded quarterly. Sadly, all of your family recently passed away due to a peanut allergy. Kind of stinks, but this leaves you as the sole recipient of the account. How much money are you worth now? So we're going to plug into the compound interest formula because it talks about compounding quarterly. So after some time passes, we have principal times 1 plus r over n raised to the nt. Now, this was in 1812. How much are you worth now? Your time is going to be 2025 minus 1812, which I feel like is 213 years. All right, hopefully you agree with me. 1 plus the rate of interest expressed as a decimal, 0.05 over n, which is 4, raised to the 4 times 213th power. And I don't know why I wrote that a there. That's not where it goes. This is the amount in 213 years, is the principal, which is 0.1. Now, I know most of you guys do not have your TI-84s. All right, so believe it or not, you can go to Desmos. You can type that stuff in. You had 0.1, 1 plus 0.05 over 4 with an exponent of 4 times 213. And it did not put that in the right spot, times. Choose parentheses here, 213. Man, I was expecting there to be more money there. I really was. Still a good chunk of change. It's $3,949.73. Now let's see if the TI-84 agrees with me. We had a tenth of a dollar times 1 plus 0.05 over 4 with an exponent of 4 times 213. And sadly it did. $3,949.73. Play along, make sure you know how to type. 394973. Okay, so that's a you try that you do, and by all means, write stuff down. Write more than an answer. All right, here comes the number E. I don't require you to know too much about E other than it's 2.72, roughly. There's a lot more to it. It's a very important number in mathematics, believe it or not. It's Euler's number. He gave it the name. It's on your calculator too, by the way. But you get a cool little formula when things are compounded. Notice what it says. Continuously compounded interest. Continuously compounded interest. You get a cool little formula. It's called PERT. Again, P is the initial amount invested. E is what we call a natural base. R is the annual interest rate written as a decimal. And A is the value of the account after T years have passed. PERT's used a lot when you do these things in science classes, your science courses. They use this form. A sub T is A subscript 0 e to the RK. They use ERK, but it's used a lot. All right, so Regina is investing $12,600 into an account that earns 3.2% annual interest compounded. See the word continuously. So because I saw the word continuously, I'm going to be using PERT. What is the value of the account after 12 years? Round your answer to the nearest dollar. So this is my principal. R is going to be 0.032 because we have to shift the decimal 2 places to make it a decimal, not a percentage. And this is my time. Time is 12 years. So the amount in 12 years is the initial value invested, 12,600, times E to the 0.032. And we have an exponent of 12, or sorry, times 12. And, you know, I'm not sure. I'm pretty sure Desmos can do this. I may have to bring up the keypad here. What do I have? 12,600. 12,600. Don't use parentheses. There should be on Desmos an E somewhere. Trig, statistics, visualizations, T-score. There's LN. That's why I'm surprised they don't have E. Well, never mind. Desmos won't do it. At least not what I'm seeing. So I'm just going to push some buttons in the old TI-84 and you should play along. So we have 12,600. There's the E key. Notice it's right by LN. I've already forgotten what the rate of interest was, 0.032. And I feel like it was 12 years. So notice I'm just typing in what I wrote, right? Press that magic enter key. $18,498.63. 18,498.63. There you go. It's not hard. The last 2 things in here are for you to try, and you need to be trying. You need to try. You do. I'm pretty sure if I put my phone in scientific notation, that it has it. Yeah, my little phone right here, it has an E key. If I could switch over the camera without making my software crash, I could show you, but even my phone has an E key. Okay? So I don't need to hear it. Like, you can do this. You may not want to, but you can do it.